Welcome to session number 2. This is our second series on casing evaluation tools. Today's session is on multi-finger calipers. A few weeks ago, we did the segmented bond tool, and if you missed that, it is on our YouTube channel. So by all means, please pop in there and take a look. You're welcome to share it around. We are trying to keep these sessions as educational as possible. Okay. A little bit about myself. My name's Steve Waringa. I'm the Business Development Manager in Canada, based out of Calgary, Alberta. And my background, I've just shy of 3 decades looking at and running cased hole logs, anywhere from wellbore integrity to production logging, to completion operations, and then finally decommissioning. So that's kind of my background, and we're going to dive right into our session today. So when we're looking at well integrity, most of the information that we follow as an industry, there are a few documents. There are some international standards that we take a look at, and then there are also local regulatory and requirements, maybe company-specific requirements, specific areas you work in. The ones that we reference in this particular session will be referencing back to ISO 16530. That's the well integrity standards. And then the other one that's fairly common worldwide and used by a lot of different regions throughout the world is the NORSOK D-010 standard. We do use the revision 4, which is post Macondo. Myself here in Canada, like I said, there's typically some localized. I reference and do a lot of analysis looking at Directive 51 injection well analysis. So that's what the document that I tend to follow when I'm looking at my logging programs and whatnot. When we're looking at casing evaluation, in respect to the ISO standard and wellbore design, casing is one of our primary barriers, as is cement that we covered with the SCBT session. When we're looking at running casing inspection logs and determining the type of log that we run, today's tools, they are looking for internal profiles and internal defects and condition of your pipe. Some of the reasons or conditions that may arrive that would cause us to run these tools, new drills, if we're looking for, especially in the world of horizontal, where we suspect some casing ovality, or we want to make sure that we don't have casing ovality issues. New drills, again, for detection of deformation. If we've got some tight spots, deformation, some compression, these tools are very good at identifying those conditions, and then we can decide how to work through those issues. Again, here in Alberta, we have some SAG-D and steam cyclic operations. So we will see some thermal changes that may affect our pipe. So casing deformation, we see some buckling or some, again, ovality. If we're looking for identifying downhole profiles, so we end up taking over a well, the records may be a little light, or we're not quite sure of the tally when things are run in. So the case inspection tools, particularly the multi-finger calipers, we can go pull a log and then identify where all the different downhole profiles, any downhole tools, bottom hole assemblies, whatnot can be identified using the caliper tools. Detection of internal corrosion and tubular damage. So if we're looking for rod damage, or we're looking for corrosive or erosive corrosion and loss of wall thickness, if we're looking for sliding sleeves, whether they're open or closed, conditions of downhole valves, etc. And inversely to that, we may be looking at some buildup. So it could be scale buildup, local mineralization, mineral deposits, some scales, some, if we've got some inflow of shale, that kind of stuff we're going to be looking at for these tools. And quite often when we go down that road, we'll use a time-based logging program where we're looking at the buildups as they go in time, and we're also looking to see if we have mitigation plans or programs in effect, are those plans being effective, and are our strategies doing what we want them to do. So we can look at these logs over a time-based period and see how well we're faring and what the expected remainder of the life of the well is before we have to intervene. When we're looking at the lifespan of a well, so the little chart here, I've got it kind of as our production goes up. I'm going to switch to my laser pointer here, sorry. As production goes up over the lifespan of the well, and then it will go back down. At the beginning, we're looking at well design, so we want to make sure that we understand the forces that we're going to be up against. We've picked the right pipe. We've got our cementing programs in place. Do our risk analysis and make sure that we're going to have the appropriate well barriers for what we're going to do with the well. Drilling and completion, case inspection tools really do come into play here, especially if we're fracking through pipe, high rate fracks. We may see some erosion issues. We may see some breakthroughs, some sliding sleeves may not be opening. We may want to look at the effectiveness of perf placement to make sure that we've got the holes where we think they are. As we put that well onto production or injection, depending on the type of well it is, we'll see that lifespan early on where we could have some high erosion rates or some corrosion issues depending on the chemical makeup of wellbore fluids. So we may have a logging program in place to monitor that. And then as the well declines, we'll typically see some changes in wellbore fluid makeup. We may see some acid gases starting to form. We may have higher water cuts. So in order to really understand how long our wellbore life expectancy is, case and inspection logs allow us to monitor the condition of that pipe and make sure that we're still in parameters when we're looking at our production. And then the final stage is the decommissioning stage. So we want to, once we're done with the well, there's no more opportunity for economic production out of it, or it's past its lifespan for injection. Then we look at decommissioning, and do we actually have the appropriate casing and cement barriers in place to make sure that we are protecting the environment from any of the downhole formations or downhole fluids, and we don't have any of those leaks coming through. Some of the conditions that we'll see as far as case inspection. So a couple of these are downhole video footage. This one here, we can start to see our casing is starting to develop rust, and so there's some general corrosion starting to happen here. If we look at this next picture down here, we can actually see there is some physical damage to our casing, and we've had some type of event come in and cause some damage. So the tools will pick that up, and we can start to understand without having to pull our tubulars. You know, if we suspect there's some issues, we go in with the tools and determine if that's an issue. The radial corrosion, again, this may be caused from turbulent flow, may be caused from, if it's a vertical, maybe some rod damage or some other effects in the well, some mechanical damage, perforating holes or perforations. We can track those. And then when we're looking at general corrosion, this one here we got from our friends over at Tenaris. This is the a really good example of mesa corrosion, which is caused typically by CO2 corrosion. So we see these very sharp-edged, deep walls, and you know, if this well had been logged with a logging program, there's a good chance that we would have picked this up and possibly been able to mitigate this issue happening and deal with it before it gets to the point where it causes catastrophic failure of our tubulars. Here's another one that occasionally shows up, and this is ringworm corrosion. So this is an effect of when the pipe is manufactured and the upsize of the end of the tubulars in order to put the threads in place and make up the connections. And that mechanical upsizing of the pipe occasionally will cause weak points, and they're high susceptibility to corrosion. So the tool can identify that, and that lets us know if we actually have a physical issue with the pipe, or if it's if indeed it is a corrosion issue, broader scale. Here's a great example. This one, when they pulled the pipe out from the outside, it actually looked like the pipe failed due to a wall crack. We can just barely see it. It's unfortunately, it's not the greatest resolution at this size, but if we crack that thing open, split the pipe and take a look, we can actually see where that full erosion went. So this was a corrosion issue, not a pipe split issue. Had, again, there been a logging program in place, we may have been able to detect this earlier on and prevented this failure of the casing and extended the lifespan before we would have had to do an intervention. When we're looking at caliper tools, they are somewhat sized to the pipe that we're running in. Spartak has 3 different sizes of tools. It's 24, 40, and 60 arms. So we have 3 versions of them. And depending on what our logging program is, or our downhole conditions, will determine which one of those tools is best suited for the operation. There is some overlap in logging sizes, so typically like a 24 and a 40 arm caliper, they can both log the same size pipe, but depending on restrictions that we need to go through, or if we have a free open wellbore, depends on which one we're going to choose for that job. When we're looking at any case inspection tool, but the multi-finger caliper in particular, quite often they're run in conjunction with other modules. So for correlation purposes, we'll run them with a gamma ray and CCL. CCL is not critical, but it does definitely help. If we're not in a premium pipe, if we're in a standard collar, typically the fingers will pick up each one of the collars, but my personal preference is I do typically like to run an additional collar locator. The tools do record internal temperature. It is part of the calibration process and analysis. When we look at it, the arms are temperature sensitive, so that has to be taken into account. But we also have the ability of adding a high resolution external temperature probe to the string. They can be run in tandem with the magnetic flux leakage tools, so the casing thickness inspection tools. That will actually be our next session, so that'll happen early in the new year. So quite often caliper tools and thickness tools are run together. And then if we're looking at full wellbore condition, these tools can also be run with segmented bond tools, so we can stack them all together. We're going to talk about some of the telemetry options going forward here later in the presentation. But if we're running something like Spartak has a hybrid telemetry that allows us to run kind of a mix of surface readout and memory, which allows us to gather much more information on one trip in the well. As far as operating, the tools are capable of either memory operation or surface readout, or like I said, with the hybrid, could be a mix of the two. And then the software acquisition packages are typically either SparWorks if we're working with memory tools, or the Warrior logging system for surface readout. Okay, don't see any questions there, so we're going to jump right into the operating principles of how the tools actually function. So as I mentioned, there are 3 different sizes of tools. Depending on which tool it is, it's going to have that number of fingers. The fingers are spring-loaded. They're feelers. Basically, they are exactly what they say they are. They are a caliper tool. So each finger will measure a radius independently, and we may have anywhere from 24 to 60 fingers depending on which tool. The range of pipe sizes that these tools will measure in their standard form is 2-inch right up to 14-inch. So the 24 arm will log as low as 2-inch pipe, where the 60 arm will log all the way up to 14-inch. Each finger is a hardened material depending on which tool it is. The sour service tool, they're actually titanium fingers. They have a radial resolution of a few thousandths of an inch and a vertical resolution of a few hundredths of an inch. Now, our vertical resolution is directly tied to the speed at which we log these. So the slower we log, the higher the resolution we're going to get. It is a time-based acquisition for the most part. Average logging speed to get kind of the optimum of speed versus resolution is typically that 10 meters per minute, which 30 meters per or 30 feet per minute, or 1800 feet per hour. That's the optimum speed, but they can be run a little bit faster or a little bit slower depending on what our objectives are for that wellbore. So when we're looking at the tools themselves, so this is the 24-arm caliper. The 24-arm caliper and all the calipers are rated to 15,000 psi, or just over 100 MPa pressure. Temperature range is sitting at 350 degrees Fahrenheit, or 175 Celsius. And the diameter of the 24-arm is 43 millimeter, or 1/11/16 inch. So we can go through a pretty small profile, typically a 2-inch pipe or smaller. The tool will, if we look at the range of the 24-arm tool, so it will range anywhere from 1.77 inch up to just over 7 inch. So 45 millimeter up to 178 millimeter is what the range of these fingers are. When we look at our fingertip spacing, so depending on the size of casing that we're in, the number of arms, our fingertip spacing is about 0.23 of an inch. And then as we max out at that 7 inch, we're up to about 0.91 of an inch. Now, if that's not enough resolution, but we still need that small tool to go through restrictions, there's always the opportunity of running multiple passes and then statistically gaining more information as those passes are run. There are sour service options available for these tools with a 718 housing and titanium fingers to withstand corrosive environments. Corrosive environments can be a little tricky. It's a lot more than just how much of any particular corrosive gas or fluid is in there. There's temperature issues to take into account, mixtures and whatnot. So if you're looking for these higher end sour service, we encourage you to talk to your local BDM or give we'll provide an email here at the end of the presentation that you can get a hold of our technical team, and we can help you navigate through those specifications and make sure we've got the right tool for the parameters that you're looking at. If we move on to the 40-arm caliper, again, it's same temperature and pressure ratings. This time the tool now goes to 73 millimeter, so 2 and 7/8 size as far as the OD of the tool itself in its closed form. It has 40 arms and is able to log from 75 millimeter up to 244 millimeters. So just shy of 3 inch all the way up to 9 5/8. If we look at our fingertip spacing again, because we've now got more arms, we still stay in that very similar range. We're at 0.22 of an inch up to about 0.75 of an inch when we're maxed out at the 9 5/8. So again, very good coverage. If we need to run more, there's always the option of running multiple passes and statistically adding to that resolution. And again, these tools are also available in those sour service packages. And then the last tool, the biggest of the group here, we have our 60-arm caliper. It is a 4-inch tool, running 60 arms this time. Our range is as small as 4.5 inch, so 114 mil, up to a 14-inch wellbore, so 355 millimeter. And then because again, we've increased the number of arms, we keep that fingertip spacing in that same range of 0.21 to 0.73 inch per finger. All right. When we're looking at these tools, so when the tools or run in. They're typically run in a closed fashion, and then they open up as we go in the wellbore. The measurements that we're gathering off the caliper tools is a min-max average borehole diameter. We will pick up a tool deviation as well as a relative bearing that are built into the caliper sections. In the telemetry sections, we have a built-in accelerometer, which adds to some logging information. We'll see actually one of the examples we have here of where that accelerometer gives us a little bit of information that we may have misdiagnosed had we not had it. We do have the internal tool temperature comes standard with it. These tools are temperature compensated, so that's a requirement of the tool. And we have the option of adding that external temperature module if we desire. If we're running surface readout, we will get a cable head voltage measurement back to surface. So if we're having some communication problems, that will allow us to know if we're having issues at the tool or if it's something going on at our surface acquisition system. So we can see that real-time tool diagnostics. As far as processing, once we get everything back to surface and process it, we can develop either 2D or 3-dimensional images after processing. So depending on the complexity of that data set, will depend on how quickly that stuff can be processed. Some of the simple 2D stuff can actually be done right on site. There is also in the analysis software, there's an eccentricity correction that can be applied so that you can, if you do have some centralization issues, the tool can be compensated for that. I do suggest you're careful with that correction. If you're working in buckled pipe or in deformed pipe, sometimes that eccentralization correction factor will try and fix things for us when they really shouldn't be fixed. And then once we get all that back, all the data sets here are typically compatible with any of the more advanced analysis packages that are available on the market today. So there's several more in-depth analysis packages that this information can be fed into and be tied together with a lot of other data sets as well. And then, as we mentioned earlier with the correlation, typically we'll rarely do we run without gamma ray. Occasionally we'll run without color locator, but they're typically in the string and used for correlation purposes. When we're looking at the finger design, the caliper tool is a spring-loaded finger. The spring load is transferred to a push rod. That push rod is then on a transducer, and depending on the force applied to the transducer, that will give us an indication of how open or closed that finger is to a very, very high resolution. So we can see, as mentioned before, hundredths of an inch variation. So very easy to see minor changes. And some of the features of those fingers, the finger width of a standard finger is 0.055 of an inch. They are hardened tips. They're rounded off a little bit, so they're not doing physical damage to the casing. So there is a bit of a radius to those fingertips. And the design of them allows for ease of field replacement. So we do have downhole environments that are hard on these fingers. Occasionally we'll see some wellbore conditions may cause some breakage or damage to the fingers. The way they're designed, the replacement of those fingers on site or in the field is actually quite easy or quite doable. It's not always easy, depends what environments we have. I wouldn't recommend doing it here in Alberta here in a couple of weeks when we are expecting our minus 40 degrees temperature and howling snowstorms. But inside of a recorder cab or a portable CCAN workshop type environment, again, those fingers can be easily switched out in field applications. Now, if there is damage to the push rod or the transducers, that is going to require the tool to go back to a tech bay for repair. And we have a couple of districts around globally as well. We offer that training to bring in-house technical teams up to speed on tool repairs and such. When we take all those fingers, so depending again on the tool, the number of fingers we have, we put those into a basket shape. So if we look at this tool here, here's each one of the fingers, and those push rods are underneath this clamshell here. So that's where we'll access those, take that clamshell off, clean it up, change out the finger, then repack it with grease and check everything out, and then put her back together. Now, as far as resolution of the tool, just like every tool out there, it has its limitations and design features. So when we're logging, we definitely want to take that into account. What are we looking for, and what can we expect from the response of the tool? So if we look at these billets, again, this is courtesy of our friends at Tenaris. A situation like this is going to be quite easily seen. Our next one, a nice smooth wall. So if we're just looking for confirmation or design of the pipe, if we suspect we have a casing size change, the tool is going to pick that up very nicely. This one here, the third in the row, we're going to see some general corrosion, but we're not going to be typically picking up all these little pits and holes, especially if they're smaller than the fingertips themselves. So although we'll see it, it may not be as accurate as a representation as what you would see on surface taking a look at it through a microscope. As far as the tool itself, when we run it, it is a modular tool, which allows it to be easily transported. So it breaks down into small packages. This particular one we have here, we have two centralizers shown. Depending on the situation and the opportunity for e-centralization, that can be ramped up. We can run multiple centralizers. So here we've got the memory section with a battery pack, or we could run the surface readout or hybrid telemetries. Then typically we will have a gamma ray CCL section. We would usually run a centralizer directly above and then directly below the caliper module. Now, the centralizers here that are pictured are the Spartak centralizers. They are a positive centralization arm design with roller bearings. We do recommend these. We do not recommend both spring type centralizers for caliper tools. They just don't have the strength to hold up in deviated situations. So these are the tools that typically will come with this this module. And then on the very bottom, we can run a bullnose. Now, if you're running in memory mode, these tools are designed to be pulled up the hole. So we look at this basket design here. It is not conducive to running down. So this tool here, we would definitely want to be running in an up position. If there are circumstances where we do need to run into a hole with memory, we could invert that tool. Something you definitely want to talk to about with your business development managers. Make sure we've helped you work through those scenarios and plan for the best data acquisition logging program that we can help you out with. So, but it is primarily a tool that's run up. Now, if we're in memory mode, those tools will open and close as per a predetermined program. So we'll look at that when we look at the memory programmable section. If we're in surface readout mode or telemetry or hybrid telemetry mode, we will send commands to the tool, and you'll be able to tell real time as the tool opens and closes. And you can open and close it as many times as long as wellbore conditions allow. So if we have debris or whatnot, they may stick in those arms. But that's the design, and they are spring loaded. So in the event we have a power failure, they don't lock open into a solid position. They are collapsible as we retrieve the tool. Calibration and verification is critical for these types of tools. Temperature really does come into a degree here that we need to characterize. So when Spartak does the full calibration of the tool, it will be done in an oven at 13 different temperature ranges. And then we use all 7 different diameters. The device that you see here, this is the calibration and field verification ring. So it's used for both purposes. It is a precision machined ring so that we can step cal or do step verifications with multiple casing sizes before and after the run, as well as during the calibration routine. What we'll end up with is 3 different reports. So we see our original calibration data. Prior to the job, we will run a pre-job verification report just to confirm that everything's in place, or if it's not, we can apply those changes to the calibration when we do the post-processing. And then again, after we've run the job, we'll run a post-verification with that same sleeve, and then get, if there's been any changes to the tool or we've seen some excessive wear, we're able to apply that to the analysis. All right, so we've looked at how the tools work and the various options of those tools. Let's take a look at some of our data sets. So when we're looking at multi-finger caliper logs, this is their standard. This is what we get in the field. This is the data that we would get on a typical surface readout or on a memory after we've downloaded and merged it with our depth files. We will see an internal and internal min, max, and average diameters. So these are calculated from the range of fingers. So a couple ways of calculating that. It may be offset fingers or it may be parallel fingers. So you have options of how to calculate that min, max, and average. It comes in very handy when we're looking at profiles and stuff. If we can see if there's ovality, that will show up on these. Our other associated curves. So as I mentioned, we have an accelerometer in the telemetry. So on this particular log, that's tucked into the depth track. And then we have our deviation curves as well as our relative bearing. So we're able to identify those high-low spots. We're able to identify dog legs, S-bends, any changes in wellbore geometry. So the tool can adjust and we can plot our post-processing appropriately and get a really good understanding of what the wellbore is actually experiencing. And then depending on the size of tool, we'll have anywhere from 1 to 24 fingers, each individually presented on the log, typically in a scale that allows them to be plotted across the screen. And we can look at those minor changes in diameter or radius. So here's an example of a log that was run in the one of the Aberdeen test wells. It's got some nice features. Just because it was a test well doesn't mean it was too easy to log. So we're going to take a look at a couple of these downhole profiles. So here we've got a 3.3 dB nipple. When we look at it on the log, if we look at our accelerometer, we do see a little bit of bouncing, but across the collar it looks pretty good. So the centralizer bounced a bit, but in the collar, or in the nipple itself, we see a very nice definition of the profile. When we see the finger curves go to the left, that means that we have had a metal gain or that the inside diameter has reduced. So it's either a buildup of minerals, but it's actually a reduction in diameter. So here we clearly see that profile in the DB nipple. When we look at the next section of the log here, we actually see a perforated pup. So when we zoom in on that, here we can see all the curves are now going to the right. So the right is a loss in diameter. So these are holes. Of course, they're perforations, so that would make sense. As we can see here, so this is a 4.5 inch casing logged with a 24 arm tool. So we can see that our resolution, our finger width is pretty good. Most of the perforations are picked up by typically 2 of the arms. So we've got some good overlap, and that'll allow us to take a really good look at those profiles when we go into our 3D analysis. And then the last one here, we've got the XN nipple here at the bottom. If we look at our accelerometer there, we can see we've got a significant amount of movement in our accelerometer. So the tool was sticking going through that. We still have a pretty nice profile of that XN nipple, but due to the fact that we know that the tool was doing some bouncing, that will allow us to take that into account when we do our post-processing. So we can clean that up a bit. We know that the tool and the depth don't necessarily jive together, so those can be adjusted. Had we not had an accelerometer on there, we'd probably be a little concerned at the profile that snipple is giving us. Hey, deformation. Some examples here of what we would look at. So this is ovality. So if we look at here, we've got each individual finger plus a heat map laid in behind just to kind of see any changes. We see the min-max average, so show us some differentials. But when we actually look at a cross plot, we can see that those differentials are in fact caused by ovality. So taking a look at that ovality calculation is very important, that we don't mistake that for defects. When we look at it in a two-dimensional, we can see that not only is it oval, but we have some buckling there as well. Here is actually one of helical buckling. So this would have been from a joint of pipe that was under compression. And once we lay that out in a three-dimensional plot, it's very clear how that buckling is affecting the pipe. And that will allow us to move forward with some well programming, how to deal with it. It might not be an issue, but it is definitely going to change some of the tools that we're going to be able to get past this section of pipe. This one here is an example of casing penetration. So when we look at the 2D plot, we can see here on each individual finger that we have an increase in diameter. So we have some metal loss. When we look at our two-dimensional heat map, yes, indeed, there is a hole there. When we look at the wire plot, we can kind of see it start to come out there, that we have some issues with our casing at that depth. When we move this into our cross plot, again, we can see very clearly that we have a profile of some damage there. And then when we move it into the three-dimensional, that profile becomes very clear. And now we can start to take a look at that data and apply it to our forensics and see if we can determine what may have actually caused this issue, or what it is. If it's getting worse, we could time base this. There are also some applications where you can take this data set and turn it into a 3D model and actually print out a copy of it at surface on a 3D plotter and or like a 3D printing machine, and actually physically get to see what that profile looks like and deal with it. I've done a few of those in the past, and it actually works quite well. The other product that we'll see come out of the caliper tools will be a graded penetration tally. For a true pipe condition tally, you're going to want to look at some type of the thickness tool. So the magnetic flux leakage needs to be put together, because we do need to make sure we don't have any exterior damage. Caliper tools will only see interior damage. So if you have exterior wall loss, so this will give us a bit of a grading. We can see what if we have internal damage, and then we can apply that. And these parameters are totally customizable to meet either your local regulatory or your internal desires for ongoing corrosion programs. And we can set those parameters, and then the program will process and provide you a tally with the different min thickness, max penetration, and all that information is tucked into an actual report. As far as deliverables, we at the field level, typically you will end up with a log. It can be plotted either in color or black and white, depending on what is available as far as plotters. Continuous logs, they can put in multiple scales. Again, that's typically processed through the Spartak or the SparWorks software, depending on which type of tool you're using. And then as well, we're able to provide full reporting. This can be third party, or we can do training in-house to get your team up to that level. And then, as I mentioned before, all this data is fully compatible to be exported in third-party analysis software. So if you're trying to add this to multiple data sets and to field analysis, then that data can be easily brought over and applied to a full database. Okay, let's see any questions so far, so let's keep going. When we're looking at telemetry options, as I mentioned, the tool has 3 different options. The straight E-line surface readout, this one's kind of starting to go into the history books. We're seeing the new hybrid telemetry start to displace the surface readout. Our limitations with surface readout is there's only so many channels and so much bandwidth that we can get up the E-line. If we start to run multiple sensor arrays and some of the higher sensor modules, such as magnetic flux tools or segmented bond tools, then the hybrid telemetry allows a limited amount of data to be sent up whole. We can maximize the bandwidth of the wireline that we're on or the conveyance, and then store full high resolution data in the tool section that's downloadable after we retrieve the tools to surface. So we can still monitor everything, make sure we're working, collecting all that data. And then the either the hybrid in full memory mode, or we can put a memory section on. Again, depending on how many tools we're looking at, then we're going to need battery power and memory to capture that. The one additional with memory tools, especially with multi-finger calipers, is we're going to have to be very diligent in figuring out our logging program so that the tool opens and closes at the appropriate times, and that our cable depth, our cable direction and speed matches those opening and closing parameters, so that we don't damage tools by running it into the hole with the fingers open. As far as acquisition systems, if we're in surface readout or hybrid mode, then we'll be using the Warrior. It's compatible with Warrior panels and software. There are several features within the Warrior software that allow cross plots and limited 3-dimensional processing real time. And then if we're running memory mode, then we flip over to the SparWorks tool communication. That's done through USB communication and a tool interface. So we can set up the program of the tool. We can download the tool, do our calibrations and verifications through the memory controller. If the wireline unit or the coil unit is so designed that it has a line system, we may be able to tie into that existing depth system. If not, we have a portable line management system that can tie into the encoders and the tension panels, so that we can measure the line conditioning, and then we'll marry that information back to the telemetry when we put everything together. Again, that's done through SparWorks, and we can generate the logs that way and then output them into for post-processing. Okay, so just a quick summary of the tools. As we mentioned, we've the 40 arm, sorry, the 24 arm, 40 arm, and then the 60 arm. So if we look at our casing ranges, we go anywhere from 177 inch, which is 45 millimeter, all the way up to that 14 inch at 355 with the different arm sizes. And again, depending on what downhole restrictions, we'll look at our tool diameters to see what we can get through. Now, these tool diameters are in closed position, so fully collapsed with the arms fully retracted. That's what those dimensions are, and will allow us to go through different profiles. And again, we've got the sour service options available. Definitely something you want to talk to your business development manager about and make sure that they are suitable for the environments. If they're not, then we may need to look at alternate designs. Okay, just some of the highlights. So again, 24 to 40 or 24 to 60 arms, hardened tips, so extended longer life for those fit tips, easily field serviced. Real-time min-max average borehole diameters, the deviation and relative bearing built in, easy disassembly and disassembly of the complete package. Everything's modular. Standard logging speeds are available. Again, those can be calculated depending on the resolution you desire. And then available right through memory, SRO, and then the hybrid telemetry packages. All right, that pretty much brings us spot in on time. That's kind of the multi-finger calipers in a nutshell. So we'd like to thank you for joining us in today's session. Appreciate your time. We do value that time, so we've tried to keep this as quick and efficient as possible. If you have any additional questions on today's tools or any of the tools that Spartak Systems has in their catalogs, by all means, please reach out to us. Our email address, if you are not already familiar with your local BDM, is sales@spartaksystems.com. We monitor those and will direct you to the appropriate person to answer any of your questions or requests. It'll either go to the business development managers or to the technical assistance team, so we can help you and make sure we've got all the right answers for you. We will be taking a little bit of a break here over the Christmas season, but we'll be back early in 2021 with our third session on magnetic flux leakage tool, so the casing inspection CIT tool, and that's again continuing with our well integrity logging tools. So again, we thank you, we appreciate your time. Glad you could join us, and hopefully you got some value of this.